Okay, so now I'm going to talk about causality, because that's the next section. So basically, what Tong says is if we have two operators, O1 and O2, and we evaluate those at two space-time points, x and y, if those points are space-like separated, then we would expect this commutator to vanish, basically saying that a measurement at x can't affect a measurement at y if they're separated by a space-like interval, which is what we want out of our Lorentz invariant theory. So if we explicitly compute, if we take for O1 and O2 our operator, our field operator that we, the Heisenberg version that we found last time, and he calls this delta of x minus y for whatever reason, whatever. But you can compute this pretty easily. You get this, which is fine. So if we assume that x minus y is a time-like interval, so if it's time-like, then that means there's some reference frame where the separation between these 2 points is only a separation in time. So I can write my x minus y in terms of this, as this. And that will pick out of our momentum just the energy part. So basically, we get this thing. And this does not vanish, which is okay because it's time-like. It's a time-like separation, so we don't need that to vanish. And likewise, we can do the same thing if our separation is space-like. Then we can write this separation as just a spatial part. And so if we plug that in to our expression, we get this. And the key difference is that now, since we pick out the momentum, the 3 momentum part with our separation, I can have these 2 integrals here. And since I'm integrating over all momenta, I can exchange p with negative p in this integral, and this integral will end up being the same as this. So these will cancel, and it will vanish, which is good. So that's nice, but there's another issue in that, so we have this other test we can do, which is basically if we have a particle at point y and we have a particle at point x, what is the overlap between those 2 states? So our field operator 5y will, acting on the ground state, will create a particle at y, and then the conjugate, which in this case, since we have a real scalar field, is just itself. If we act on the left, that will create a particle at x, and so this will be just inner product of the state with one particle at x, one particle at y. And so we would expect, again, if x and y are space-like separated, then this should be 0. So to evaluate this, you can just write the expressions, and so we'll have 2 integrals, kind of what we've been doing. And there will be 4 terms basically involving the raising and lowering operators. The only non-vanishing one will be where you have a raising operator acting on the right and a lowering operator acting on the left. Otherwise, you will annihilate these ground states. And then this is just, if you act a raising operator on the ground state, you get just our 1 particle states. And using our normalization that we've defined a few videos before, we know this is equal to this. And so if we plug that in here, then we can do this integral, or one of the integrals rather, and we get this, which he calls d of x minus y. And so then he says if it's space-like separated, then d of x minus y, it vanishes exponentially outside the light cone, but it isn't zero. So that seems kind of bad. Actually, it's kind of like in ordinary quantum mechanics, where in like a classically, forbidden region, the wave function vanishes exponentially. Here, outside the light cone, this overlap, this amplitude, vanishes exponentially. And so that seems bad. But if we look at our earlier calculation, this commutator thing, we can write that our term, this d of x minus y, well, this is just, remember, our commutator expression ended up being two terms that were basically that. So this commutator, x minus y, is just d of x minus y minus d y minus x. And those did cancel. That was 0. So I'm just going to read what Tong says about that because, I can't put it any better kind of way. So yeah, there are words you can drape around this calculation. When the interval is spacelike, there is no Lorentz invariant way to order events. If a particle can travel any spacelike direction from x to y, it can just as easily travel from y to x. And at any measurement, the amplitudes for these two events cancel. With a complex scalar field, it's more interesting. We can look at the equation, this thing outside the light cone, and the interpretation is now that the amplitude for the particle to propagate from x to y cancels the amplitude for the antiparticle to travel from y to x. And in fact, this interpretation is also there for a real scalar field because the particle is its own antiparticle.